Hello everyone, myself PIYUSH and TANDEL, working as Assistant Professor in Electrical Engineering Department of Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. And the name of subject is Industrial Instrumentation, which comes in 4th year, 7th semester. Today we are going to discuss the chapter number 2, that is strain gauge and strain measurement. And this is the module number 2.2. Now starting with the flow of content, over here we are going to study about types of electrical strain gauge. Right now we are dealing with types of strain gauge. In video lecture 2.1 we already study about the mechanical and optical type strain gauge, and here we are going to discuss in detail about the electrical strain gauge. Now in electrical strain gauge we are going to study about different types, that is the resistive strain gauge and gauge factor. So what is the resistive strain gauge? We have two different type of resistive strain gauge, that are the unbounded resistance wire strain gauge and the second one, that is the bounded resistance wire strain gauge. And in the last we are going to study about the gauge factor. So starting with the type of electrical strain gauge, which are different types of electrical strain gauge. So we have total number of 8 different type of strain gauge. The first one, that is the unbonded resistance wire strain gauge. Second one, that is the bonded resistance wire strain gauge. In this video lecture we are going to study about these two different type of resistive type strain gauge. So these two are comes in the resistive type strain gauge. Then after grid type strain gauge, and after that torque type strain gauge, helical type strain gauge, reset type strain gauge, bonded metal foil strain gauge, and in the last, that is the semiconductor strain gauge. So we are going to discuss all this in detail now. So starting with the resistive strain gauge. So in resistive strain gauge we are going to study the unbonded resistance wire strain gauge, and second one, that is the bonded resistance wire strain gauge. So starting with the unbounded resistance wire strain gauge. So this is how our unbounded resistance wire strain gauge is going to be look like. An unbounded strain gauge comprises of a wire that is stretched between 2 points in an insulating medium. So in insulating medium we have our 2 point that is connected with the resistive wire. So over here, as we can see, black line, that is our resistive wire, and these are the points, and this is the complete metal ring. Okay, and whenever we are applying the force in this direction, at that time this shape of this ring is going to be changed, and according to that the resistive wire, the dimension of this resistive wire is going to be changed. Either it can be tensile force or compressive force. Depending upon that, the area and the length of this cable is going to be changed, and according to that we can measure the resistance of this cable and define the amount of force that is applied on this instrument, right? Next, a bridge is balanced when no load is applied. Okay, over here as we can see, bridge is balanced. It means we have total 4 different resistance wire over here. This is the stretch unbounded strain gauge. Okay, these are stretched, there are no sag in between these 2 points, and these are in complete tension right now. Okay, and this is the movable part, or whenever we are going to apply any kind of force over here on this point. Okay, generally the wire are kept in under tension, hence there is no free vibration and no sags. Okay, the resistance of the strain gauge change when external load is applied. From this point, whenever we are going to apply any kind of force, the resistance of the cable is going to be changed. This cause an imbalance of the bridge circuit, producing an output voltage. So it is going to produce some output voltage because the bridge is not going to be in balance condition, right? This output voltage is proportional to the amount of strain. Using unbounded wire strain gauge, we can detect the displacement up to 50 micrometer. Okay, we can measure the displacement up to 50 micrometer with the help of this type of unbounded strain gauge. Now next one, that is the bonded resistance wire strain gauge. A fine wire element that has a diameter of about 25 micrometer, over here 25 micrometer, is looped back and forth on a base mounting plate. A plank is cemented on the member undergoing stress. Okay, let's see the figure first. the bounded resistance strain gauge is going to be look like this, and here we have our cable that is wounded back and forth on the plank and it is cemented on this. Okay, now moving forward, the grid of the line wire is cemented on the carrier. A carrier may be a truss sheet of Teflon, bakelite or paper. Okay, the top of wire is covered with a thin material, so the wire is not mechanically damaged. Okay, over here we have a top that is mechanically covered with a thin plate. Okay, because we cannot damage our cables or wires through our force. And second reason is that the force that is applied on this gauge is uniformly distributed. That's why we require to cover the top with the material, thin material. Stress is distributed uniformly as the wire is spread. Okay, then after, the resistance of the conductor is expressed as, okay, any resistance, we have the resistance of the conductor, that is R is equal to rho L by A. Over here A is the area of the conductor, and we can further define A is equal to pi R square or pi D square by 4, right? Because D is the diameter and R is the radius, so R is equal to rho L by A. Now moving forward, we are going to see the gauge factor. Okay, this is very important term with respect to your theory and in your examination also. The gauge factor, that is GF, is defined as the unit change in resistance per unit change in the length of string wire. Okay, gauge factor is defined as the unit change in resistance, that is delta R by R. So over here delta R is the change in resistance divided by the actual resistance before force is applied on the gauge. Okay, so this is the unit change in resistance, and unit change in length, that is delta L by L. So over here delta L is the change in length after application of the force, and L is the actual length before the force. So it is called as a unit change in length, that is this gauge wire. Okay, and it is mathematically expressed as GF is equal to delta R by R divided by L, right? Now we are going to talk about the gauge factor. The gauge factor, that is GF is equal to delta R by R divided by delta L by L. So it is defined as unit change in resistance per unit change in length. So now we are going to derive this equation. Before that, we know that delta L by L, that is our strain force. So we define our strain force is equal to delta L by L. So putting this value into the GF equation, GF is equal to delta R by R divided by strain, right? Now we can give this equation number 2 and this equation number 1. Okay, this equation number 3. Okay, so GF is equal to delta R by R divided by E. Now we are going to see the equation of resistor. How we are defining our resistor? R is equal to rho L by A. Over here rho is the resistivity of any material. Depending upon the material, resistivity can be changed. Then after L, that is the length of our conductor, and A, that is the area of our conductor. Now we know that if we have our conductor, then the area of that conductor we can define as pi r square, right? So we can write like rho L pi r square. But we know one thing, that is R is equal to D by 2. So R is the radius of our conductor and D is the diameter of the conductor. So we can write like R square is equal to D square by 4. R square is equal to D square by 4. So putting this value, rho L divided by pi D square by 4. So this is our equation of R, that is the resistance. Whenever we are not applying any kind of stress or strain or any kind of force to our material, at that time our resistance is going to vary with its rho, then after the length of the conductor, and divide by the pi d square by 4. Now suppose if we are applying some amount of force, let's say we are applying strain type of force, at that time what's going to be happen? If we have our conductor and we are applying strain type force, its length is going to be increased. Its length is going to be increased, and at the same time its diameter is going to be reduced, right? Its diameter is going to be reduced and its length is going to be increased. So after applying the force, we can write the equation of R, that is R dash is equal to rho. Then after land is going to be increased, that's why we are writing L plus delta L. Over here we are writing plus because the land is going to be increased. At the same time, pi by 4 d square. So it is change in diameter. So diameter is going to be reduced, right? So we can write like d minus delta d whole square. Okay. Now further we can define this equation like rho L plus delta L divided by pi by 4 d square minus twice d delta d plus delta d square. Okay. In this equation we have delta d. So the value of delta d, that is the change in diameter, that is very small. So we can neglect this term because it is very small. So we can neglect this term of delta d. So again we can write like R dash is equal to rho L minus L plus delta L divided by pi by 4 d square minus twice d del d. Okay. Okay, now taking the common L from the upper side and taking d square from the lower side, rho L 1 plus delta L by L and divided by pi by 4 d square 1 minus twice delta d divided by d, right? So this is our equation of R dash, that is change in resistance. Whenever we are applying some amount of force, this is the equation of change in resistance. Now we need to remember the Poissions ratio. What's the Poissions ratio? Suggest us. Okay. So Poissions ratio is defined by change in diameter by change in length. So Poissions ratio is defined as delta d by d divided by delta L by L. Okay. So this is how we define our Poissions ratio, that is change in diameter divided by the unit change in length. Now again, putting this value, we can get, if we want to put the value of Poissions ratio inside of this equation and putting the value of delta d by d, we can derive like delta d by d is equal to Poissions ratio, that is V into delta L by L. So putting this value into the equation of this, we can get R dash is equal to rho L 1 plus delta L by L divided by pi by 4 d square 1 minus, now what is the value of delta d by d? That is this value. So twice V delta L divided by L, right? So this is how we can put the value of Poissions ratio inside of our resistance equation. Okay. Now multiply both the sides with 1 plus twice V delta L by L. So we are multiplying both the sides with 1 plus twice V delta L by L. Okay. 1 plus twice V delta L by L. So now multiplying both the equations, we can get rho L 1 plus twice V delta L by L plus delta L by L plus twice V delta L square divided by L square, and in denominator pi by 4 d square. Now multiplying both the term, 1 minus 4 V square delta L square divided by L square. Now again the value of delta L, that is the change in resistance. So the power of change in resistance is going to be reduced. So we can neglect this term also of the delta L square, because power of delta L is going to be reduced and we can neglect that term, and again writing something like rho L 1 plus twice V delta L by L plus delta L by L and divided by pi by 4 d square. Okay, we can also neglect this term. So this is the equation we can get from neglecting the value of delta L by L. Okay, now we can take common delta L by L from this equation, right? So we can write like R dash is equal to rho L 1 plus delta L by L twice V plus 1 divided by pi by 4 d square.
So this is the equation of change in resistance. Whenever we are going to apply any kind of force, that is tensile or compressive, at that time we can experience this type of change in resistance. Now we can also derive our change in resistance R dash is equal to R plus delta R, right? Because delta R, that is the change in resistance, and delta R, that is the change in resistance after applying any kind of force. This is the actual resistance, that is the before applying any kind of force. So this is the equation of R dash is equal to R plus delta R. So if we need to define the delta R value, at that time we need to derive the equation, that is rho L 1 plus delta L by L twice V plus 1 divided by pi by 4 d square is equal to R. R, that is our rho L by A, rho L by A, that is the pi d square by 4, right? Plus delta R. Now if we can multiply this equation, rho L by pi by 4 d square plus rho L divided by pi by 4 d square delta L by L 1 plus twice V is equal to delta R. So this is the change in resistance. So equation of change in resistance, delta L by pi by 4 d square by 4 plus delta R. So over here this equation is going to be cancelled out because it is going to be minus. So this is the equation of our delta R, that is the change in resistance. So we can write like delta R is equal to rho L by pi by 4 d square delta L by L 1 plus twice V, right? And this is the equation of our resistance. So we can write like delta R is equal to R delta L by L into 1 plus twice V, right? Now taking this value of R on this side, delta R by R is equal to delta L by L 1 plus twice V, and again taking this L by L on this side, we can get delta R by R divided by delta L by L is equal to 1 plus twice V. But what is the value of delta R by R divided by delta L by L? That is our gauge factor, that is GF. So we can write like GF is equal to delta R by R divided by delta L by L is equal to 1 plus twice V. So this is the equation of gauge factor in form of Poisson's ratio. So we can also define our gauge factor in the form of Poisson's ratio. And Poisson's ratio for metal lies between 0.25 to 0.35, and hence the gauge factor would be in the range of 1.5, because if the Poisson's ratio is multiplying with 2 and increasing with the 1, so gauge factor is going to be range in between 1.5 to 1.7, and strain gauge have a very high sensitivity, so gauge factor is defined very accurate result to us. Thank you.
Now here is the difference between unbounded and bounded type strain gauge. So bounded strain gauge and unbounded strain gauge. In bounded strain gauge, the bounded resistance wire strain gauge are bounded with cement on the surface, and on the other hand an unbounded strain gauge comprised of a wire that is stretched between 2 points in an insulating medium, that is air, right? And a fine wire element that has a diameter of about 25 micrometer is looped back and forth on the base of mounting plate. The plate is cemented to the member undergoes to stress. And on the other hand, in unbounded strain gauge, the diameter of the wire is approximately 25 micrometer. The unbounded strain gauge are concentrated in a bridge circuit. Okay, we need to remember this. Unbounded strain gauge are concentrated into the connected in the bridge circuit. These are some questions from the GTU with respect to which are very important with respect to your examination. So please note this down, which we already covered in this video session, right? And thank you. If you have any kind of queries regarding this session, please feel free to ask me in comment section. Thank you.